Okay, good day class. This is the chapter 7 of our discussion, the control unit. Okay, in this chapter we will discuss the micro operations of a control unit, the control of the processor, the hardware implementations. Okay, under the micro operations, we will discuss the 4 registers to fetch in the fetch cycle, the fetch cycle sequence, the indirect cycle, the interrupt cycle, the execute cycle, and the instruction cycle. Under the control of the processor, we will discuss the functional requirements of a processor, three-step process, the control signals, and under the hardware implementations, the control unit inputs and the hardware solutions. Okay, let's go with the micro operations. As we discuss further in our lessons, we've seen that the operation of a computer in executing a program, it consists of um, a sequence of instruction cycles with one machine instruction per cycle. And of course, um, we need to remember that this sequence of instruction cycle is not necessarily the same as the written sequence of instruction na kung saan it makes up the program because of the existence of the branching instructions. Repairing here is the execution time of sequence ng isang instruction. And to design a control unit, however, kailangan nating i-break down yung description further ng isang control unit. And we will need to see that each of these small cycles na involved dun sa series of steps, each of which involves the processor registers. And we will refer to this step as the micro operations. The word micro is a prefix word that refers to the small, or each step that is very small and accomplish very little. In this diagram, it shows the relationship among the various concepts of um, what we discussed dun sa ibang lesson. And to summarize that, the execution of the program consists of sequential execution ng mga instructions. And each instructions, it is executed during the instruction cycle na kung saan it made up of short sub-cycles. Na kung saan ito yung fetch, indirect, execute, interrupt, and other sub-cycles. Na kung saan the execution of each sub-cycles involves one or more shorter operations. And that operation is the micro operations. We now begin to look at the fetch cycle in which it occurs at the beginning of each instruction cycles, and it causes an instruction to be fetched from the memory. Meron ditong 4 registers na involved dun sa fetch cycles. First is the memory address register or the MAR. the memory buffered register or the MBR, the program counter or the PC, and the instruction register, the IR. Again, the MAR or the memory address register is connected to the address line of the system bus, and it specifies the address in the memory for the read and write operations. Sa memory buffer register naman, yung MBR, connected dito dun sa data line of the system bus, and it contains the value na i-store dun sa memory, or it holds the value of the last read from the memory. Yung PC or yung program counter, siya naman yung nag-hold ng address for the next instruction to be fetched. At yung instruction register naman, yung IR, it hold the last instruction na na-fetch. And that is the 4 registers na involved dun sa fetch cycles. And therefore, the simple fetch cycle actually consists of 3 steps. 3 steps and 4 micro operations. And each micro operations ay involved dito yung movement of data into or out of the registers. As long as these movement do not interfere with one another, several of them can take place during one step, and it saves time. And we can write this sequence of events as this image, or as this sequence follows. This events of sequence follows. The group of micro operations must follow two simple rules. First is the proper sequence of event must be followed. That is the first rule. The proper sequence of event must be followed. Though, so the MAR here from the PC, the MAR from the PC must precede to the MBR from the memory. Again, the MAR is the memory address register na kung saan siya yung nag-specify ng address from the address ng memory na i-read or i-write. And the PC is holding the address of the next instruction. Ibig sabihin, from PC na nag-hold ng address, papunta kay MAR na siya yung mag-specify ng address na manggagaling kay program counter. Then, the from the memory, yung magiging yung address from the memory, it will the memory buffer register will fetch the value that contains in the memory. Because the memory read operations makes use of the address in the MAR. Number 2 rule. Number 2 rule is to if conflicts, the conflicts must be avoided. Conflicts must be avoided. One should not attempt to read to or write from the same register in one time unit. Kasi the result would be unpredicted. Pag nangyari yung napalitan yung or na-rewrite yung memory nare-write yung naka-load dun sa register. For example, the micro operations from the MBR to the from memory to MBR and the MBR to IR, ito, should not occur during the same time unit. Kaya kung mapapansin nyo, first, yung time, second time, nauna si memory from the MBR, then the third time is si MBR to IR. Hindi pwede sila magsabay kasi nga, mag-hold pa lang ng value si MBR from the memory. And from MBR, si instruction register will hold the next instruction. Na kung saan din the next instruction will be fetched from the program counter. Kaya nandito mauuna si program counter dito. And the final point, final point worth nothing is the one of the micro operations that involves in the addition. And to avoid duplication of circuitry, this addition should be performed by the ALU, arithmetic logic unit. And the use of the ALU may involve additional micro operations depende dun sa functionality ng ALU na and ng ALU and the organization ng isang processor. Okay, let's go with the indirect cycle. Kanina yung fetch cycle, ngayon naman indirect cycle. Once an instruction is fetched, the next step is to fetch source operand. Yung magiging operands natin for the operation. And continuing our simple example kanina, let us assume one address instruction format with a direct and indirect address that allowed dun sa instruction. And if instruction specifies an indirect address, then the indirect cycle must precede the execution cycle. And the data flows differs from somewhat from that indicate in this diagram. The data flow here in the indirect cycle, and the address field of the instruction is referred to the MAR from the IR instruction register, and then it used to fetch the address of the operand. And then finally, the address field of the IR is updated from the MBR, so that it now contains a direct rather than an indirect address. Let's go with the interrupt cycle. The interrupt cycle, at the completion of the execution cycle, a test is made up to determine whether any enabled interruption have occurred. If so, the interrupt cycle occurs. And the nature of the cycle varies greatly from one machine to another. We present a very simple sequence of events that can be show, or it can you can see in this illustration. This is the sequence from the interruption cycle and data flow. In the first step, the uh, the con the content of the PC are transferred dun sa MBR. Yung last instruction, the next instruction from the PC will be transferred dun sa MBR na kung saan siya yung kukuha ng value from the memory so that they can save uh, they can be saved from the interruption. Then the MAR is loaded with the address at which the content of the PCR that be saved. And the PC is loaded with the address um, of the start of the interruption process routine. So yon. And these two action may each be a single micro operations. These two operations. However, because most processor provides multiple types or level of interruption, it may take one or more additional micro operations to obtain the save address and the routine address before they may be transferred to the MAR and to the PC. In any case, once it is done, the final step is to store the MBR na kung saan it contains the old data or old value from the PC into the memory. It will save the value dun sa memory from the MBR to the memory. And the processor is now ready to begin the next instruction cycle. Next is the execution cycle. The fetch, the indirect, and the interrupt cycle are simple and predictable. And each involves a small fixed sequence of micro operations, and in each case, the same micro operations are repeated each time around. This is not true in the execution cycle. Kasi there are variety of codes na kailangan, and there are number of different sequence of micro operations that can occur. And the control unit examines the opcodes and the generated sequence of micro operations na based dun sa value ng opcodes. This is referred to as the instruction decoding. Let us consider several example. Let's consider to add instruction, the add instruction na kung saan this add instruction will generate an operation for the R1, then the X. Ibig sabihin, we will add the value of R1 sa X. Na kung saan the X is located dun sa memory and the R1 is located to the register. And this is the sequence of the operations, the micro operations. From the IR, from the address, it will go to the MAR. Then from the memory, it will get the from the IR again, from the next address, next instruction, that will get the add instruction to the MAR, the MAR will hold the will specify, or it will be the one who specify the operations that hold by the IR. That will be the add operation. Then from the memory, the MBR will hold the value of X. This is the X from the memory. Then the R1 will be the value of R1 will be held from the register. Kaya kung mapapansin nyo dito, from the MBR, then i-add sa R1, then ma-hold yung value niya to R1 from the program count, from the register. Then we begin to add that will be the end of the instruction. Here the instruction here loaded to the ALU, to the arithmetic logic unit, na kung saan the ALU will execute the add operations. And this is a simplified example of a micro operation. Another is, I will erase this. Another example, another micro operations by that require micro operation to the register from the IR, from the IR to the ALU. Let us look to this example from na kung saan it is a common instruction to increment 1 then skip 0. In here, we will get the operation from the IR, or the next instruction from the IR to the MAR that will hold the next instruction. Then from the memory, the MBR will get the value that will hold the value for the operation. Then the MBR will increment 1 until the it will loop later on. Then it will skip the value of 0 here. After the increment of 1, the MBR will be the value of MBR will be transferred to the memory. Then the passive then once it transferred the value of to the memory, the MBR will be the value of MBR will be 0. Then after that, if the MBR is 0, then the PC will now hold the next instruction from the next operation. Then the PC before the instruction next instruction to be fetched, it will increment by 1, or it will be incremented if the MBR is 0. Then it will be loaded to the PC. And this test can this test and action can be implemented as one micro operation. Note that this micro operation can be performed during the same time unit during which the updated value of the MBR is stored to the memory. Next, the instruction cycle. The we have seen that each phase of the instruction cycle can be decomposed into a sequence of micro operations. In our example, kanina, there is one sequence each for the fetch, for the indirect, the interrupt cycle, and for the execution cycle. And there is one sequence of micro operations for each of codes. And to complete the picture, we need to tie sequence of micro operations together, and this is shows in this illustration. We now assume a new 2-bit register called the instruction cycle code. Ito. And this ICC designated the state of the processor in terms of which in which portion of the cycle it is in. From the fetch, indirect 01, 00 for the fetch, 01 for the indirect, 10 for execute, and 11 for the interrupt. That number represent binary. 00 is 0, 01 is for 1, 10 is for 2, and 11 is for 3. And in this flow chart, it defines the complete sequence of micro operations depending only on the instruction sequence and the interrupt pattern. And of course, there is a simplified example of the operations. The flow chart for an actual processor would be more complex. Mas complex siya kaysa dito. And in any case, we have reached the point in our lesson that the operation of the processor is defined as the performance of the sequence of micro operations. Now, we can consider how the control unit cause the sequence to occur. Let's go with the control of the processor. For the control of the processor, as the result of our lesson in the in our previous lessons, we have decomposed the behavior of functioning of the processor into micro operations. And by reducing the operations of the processor to its most fundamental level, we are able to determine define the exact control unit that cause it to happen. So we can define the functional requirements for the control unit. Those functions that the control unit must be that needs to be performed. And here are definition of these functional requirements to the basis of the design implementation of the control. There are three there are 3 steps process to the characterizations of the control unit. First is to define the basic element of the processor. Number 2 is describe the microoperation that the processor perform. And last is to determine the functions that the control unit must be performed to cause the microoperations to be performed. Okay, let's go with the first step. Ay, first and second step. Dahil we perform these steps, we now summarize the result. First is define the basic element of the processor. Here, we define the ALU, the register, the internal data path, the external data path, and the control unit. And the execution of the program consists of operations involving these processor elements. As we seen in the operations that consist of the sequence of micro operations. Now we can answer the second process. In this, as we describe the micro operations that the processor perform, the result is the number 1, transfer data from one register to another. Number 2, the transfer data from the register to an external interface like the system bus. Number 4 is the transfer data from an external interface to the register. And last is the it perform an arithmetic or logic operations using the registers for the input and output. And all of the micro operations needed to perform one instruction cycle, including all of the micro operations to be executed every instructions in the instruction set that may fall into one of these categories. Now, we can somehow show about the way of the control unit functions. Then, now we can now answer the we can now proceed with the third process. Determine the function of the control unit that must be performed. Determine the function that the control unit must perform to cause the micro operations to be performed. There are 2 basic tasks of the control units performed. First is the sequence and the execution. For the sequencing, the control unit cause the processor to step through a series of micro operations in the proper sequence. This is based on the program that being executed. For the execution, the control unit cause each micro operation to be performed. As we define the elements of the elements that make up the processor, like the ALU, the register, and the data path, now the micro operations that are performed dun sa processor. For the control unit to perform these functions, it must have inputs to allow that allows to perform or to determine the state of the system, and output that allows it to control the behavior of the system. These are the external specification of the control unit. Internally, the control unit must have the logic required to perform the sequencing and the execution function. In this diagram, we can see the block diagram of a control unit. From the instruction register to the control unit papunta sa system bus or the control bus. And this is the general model of a control unit that showing all the inputs and the output. For the input, we see that we have the clock, we have the plugs. Another is yung the instruction register here. And the control signal from the signal bus or from the control bus, this one. That is all our inputs. And the output is the control signal from the CPU or from the control unit or the processor. Ayan, ito yon. Then the control signal to control bus. Okay. Now we define the inputs and the outputs. Again, the inputs is the clock, the instruction register, the plugs, and the control signal from the control bus. For the output, we have the control signal within the processor and the control signal to papunta sa control bus. For the clock, for the input of the clock, this shows how the control unit keeps time. And the control unit cause one micro-operations or a set of simultaneous micro-operations that need to be performed for each clock pulse, yung ticking of clock. And this somehow refers to the processor cycle time or the clock cycle time. For the instruction register, the opcodes in the addressing mode of the current instructions are used to determine which micro-operations to perform during the instruction cycle. For the plugs, these are needed by the control unit to determine the status of the processor and the outcome of the previous ALU operations. For example, yun sa increment of the MBR that skip the zero. Need the zero instruction. Skip zero instruction. The control unit will increment the program counter if the zero plug is set doon sa instruction. Okay, next is the control signal from the control bus. Here, the control bus portion of the system bus provides signals for the control unit. For the output, first is this control signal within the processor. There are two types of control signal. Those that cause data to move from one register to another, and the other type is the one that activates specific ALU functions, the arithmetic logic unit functions. Next is the control signal from to control bus, papunta dun sa control bus. These are also have two types. First is the control signal to the memory, and the other one is the control signal to the input-output modules. There are three types of control signal controls that used in this input and output. Here, there are those um, there are those control signals that activates an ALU functions. Pangalawang type is that those signals that activate a data path, and last is those signals that are signals on the external system bus or the external interface. And all these signals, these three signals, are ultimately applied directly as binary inputs to the individual logic gates. Now, let us consider again the fetch cycle to see how the control unit maintains control. The control unit keep tracks of where it is the instruction cycle works, and at a given point it knows that the fetch cycle is to be performed next. The first cycle or the first step is to transfer the content of the PC to the MAR or dun sa memory address register. Then the control unit does this by activating the control signals that opens the gate between the bits of the PC and the MAR. And then the next step is to read the word from the memory or the data or the value from the memory into the MBR. Then the increment of the after that the increment of the PC. Then it will now again cycle or back to the first step of the cycle. That is the fetch cycle performed in the processor or from the control unit. And the control unit send the following control simultaneously. Number one, a control signal that open gates allowing the content of the MAR into the address bus. The memory reads control signal on the control bus. Then, a control signal that opens the gate allowing the contents of the data bus to be stored in the MBR. Then the last signal is the control signals to logic that add 1 to the content of the PC and store the result back to the PC or the program counter. And that is for the control signals. Let's go for the hardwired implementations. We have discussed the control unit in terms of its input, in its output, and the functions. Now, let's turn the topic of the control unit implementation. A wide variety of techniques that had been used, and there are these and these techniques falls into one or two categories. Number one, the hardwired implementation and the microprogram implementation. We will now focus for the first category, the hardwired implementation. In the hardwired implementation, the control unit is essentially a state machine circuit. It is a state machine circuit, and its input logic its input logic signal are transformed into a set of output logic signal, and which there are control signals. The key in the inputs are the IR, or the the instruction register, the IR. The another is the clock, the plugs, the control bus signal. That is the four inputs na diniscuss natin kanina. Again, the four inputs is the IR, the instruction register, the plugs, the clock, and the control signal from the control bus. And in the case of the plug and the control signal bus, each individual bits typically have some meaning. Example, the overflow. The other two inputs, however, are not directly useful for the control unit, the IR and the clock. First, we consider the IR. The control unit makes use of the opcodes that will perform for the different actions. For example, issue a different combination of control signals uh, that perform for different instructions. And to simplify the control unit logic, uh, there should there should be a unique logic input for each of codes. And um, this function can be performed by a decoder. It can be performed by a decoder, which it takes an encoded input and produce a single output. In general, the decoder will have binary inputs, n binary inputs, ibig sabihin, numerous numbers, numerous uh, numbers of binary inputs, and 2n binary output. And each of the 2n different input pattern will activate a single unique output. Here, it shows in this table, shows an example of n is equal to the 4 input. And the decoder of the control unit will typically have to be more complex than dun sa process. Dun sa accounts for the variable length of the opcodes. And the clock portion of the control unit issues a repetitive sequence of pulse. It issues a continuous sequence of pulse, and this is useful for the measuring of the duration of the micro operations. Essentially, the period of the clock pulse must be long enough to allow the propagation of the signal along data paths through processor circuitry. However, as we seen in the control unit, it emits different control signals at different times that within a single instruction. single instruction cycle. So, we would like to counter as an input to the control unit with a different control signals being used in the um, time 1, time 2, and so on. Doon sa mga cycles na na-discuss natin kanina. And at the end of the instruction cycle, the control unit must feedback to the counter or dun sa program counter to reinitialize at the time 1 dun sa another cycle ng instruction. And to determine the hardwired implementation of the control unit, all that remains is to discuss the internal logic of the control unit that produces output control signals as a function of its instruction or to its input cycle input signals. Now let us consider a single control signal, AC5. This is a control signal. And this signal causes data to be read from the external data bus into the MBR. Let us define two new control signals, the P and the Q. This is the new control signals, the P and the Q. First, we have the control signal C5. Then we have the new control signals P and Q that have the following interpretations. First is the 00 for the fetch cycle. Ito yung diagram kanina. Ito. Okay. First is the for PQ for the 00 fetch cycle. Ito. Now it will now process the fetch cycle until it cycle again to the dun sa control unit. Pabalik dun sa instruction cycle code. Then the PQ will go to the indirect 01 to the execute cycle, then the interrupt cycle. And the following Boolean expressions defines this one. This one. And that's it. The control signal C5 will now asserted during the second time unit of both the fetch cycle and the indirect cycle. And this expression is not complete. C5 is also needed during the execution cycle. For our simple example, let us assume that there are only 3 instructions that reads from the memory: the LDA, the add, the ADD, and the AND. Now we can define this process. This same process could be repeated for for every control signal generated by the processor. And the result would be a set of Boolean equation that defines the behavior of the control unit. And so and the control unit and the uh, processor. And to tie everything together, the control unit must control the state of the instruction cycle, as we mentioned at the end of the of each sub cycle, the fetch, indirect, the execute, and the interrupt. The control unit issues a signal that causes the timing generator to reinitialize and issue another cycle to the T1, to the time 1. And the control unit must also set the appropriate values for the P and Q to define the next subcycle to be performed. The task of implementing a combinational circuit that satisfies all this equation becomes extremely difficult. And the result is that a far simpler approach, knowing a micro programming that uses in the task. Um, and that is the end of the chapter 7. If you have questions regarding the discussion, uh, again, you can message me for the uh, for the questions, and I will answer your questions um, for your questions. Okay? See you on next week, and uh, see uh, see you on 29 for the chapter 8 of our discussions, and um, I will adjust the quiz for chapter 7 and chapter 8. And God bless you all. Ingat kayong lahat.